Let's talk about position versus time graphs. These are tricky. If you've never seen these can be really tricky, but physicists love these, teachers love these, they're on lots of tests. Why do so many people love these things? Because you could compact a ton of information about the motion of an object into this small little space right here. You basically specify the entire motion of the object, and you didn't even have to write an equation or say a bunch of words. It's all just right here. So these are actually really handy. You should know how to deal with these. So this graph represents the motion of an object, and instead of just saying object, let's make it specific. Let's say it's a turtle. A turtle, not just any turtle, a turtle with a jetpack on this turtle's back. And I don't want a sternly worded letter. I don't want a bunch of nasty comments. Let's put a helmet on this turtle. Ooh, it's a pink helmet. She's pretty. And now we got turtle safety. You always got to use rocket safety. All right, so let's say this turtle's moving around and this graph represents the motion of this particular turtle. The first mistake a lot of people make is they think that, well, maybe the shape of this graph is the same as the shape the turtle takes through space, right? So maybe the turtle went forward and then down and then up, but that's not right. In fact, turns out that's not even close. To figure out what this graph actually says, let me lay down a horizontal axis here. This axis is going to represent the horizontal position. So I'm going to label this X, and it's going to be measured in meters. And I'm doing that because, look, over here, what we're graphing, in this case, I wrote it as X. So this is going to be the horizontal position of the turtle. So the horizontal position is what we're actually graphing. What that means is, if you find the turtle at some point over here at X equals 2, then the graph should represent that the turtle is at X equals 2 by showing the value is 2. So somewhere at like 2 and a fourth seconds, this turtle was at 2 meters. And that's what this graph is going to tell you. So let's just read this graph and figure out what this particular turtle did. If this turtle didn't go forward, down, and up, what did this turtle do? Well, we'll start at t equals 0. We'll go up from there. And at t equals 0, the value of this graph is 3. And the value of this graph is representing the horizontal position. So the value of the graph is giving you the horizontal position. So at t equals 0, the turtle is at 3 meters. So let's put her over at 3 meters. She starts over here, 3 meters at t equals 0. Now what happens? So at t equals 1 second, same thing. We read our graph by going up, hit the graph, then we go left to figure out where we're at. Again, turtle's still at 3. At 2 seconds, we come up, hit the graph, we come over to the left to figure out where we're at. This turtle's still at 3 meters. That's awkward. This turtle didn't even move. For the first 2 seconds, this turtle's just sitting here. So a straight line, a horizontal line on a position graph represents no motion whatsoever. There was no motion. This is awkward. Turtle was probably trying to figure out how to turn on her jetpack. Should have read the instructions. Sorry. All right, now what happens? Turtle at some later time, 4 seconds, is at -5 meters. That's all the way back here. So between 2 seconds and 4 seconds, this turtle rocketed back this way. That's also awkward. Turned on the reverse booster. What a noob. Oh, turtle. Here we go. Made it all the way back to here. Then what's the turtle do? After that point, turtle rockets forwards, makes it back to 0 at this point, and then all the way back to 3 meters. So this turtle rockets forward back to 3 meters. That's what the turtle did. That's what this graph is representing, and that's how you read it. But there's more than that in here. I told you there was a lot of information, and there is. So one piece of information you can get is the displacement of the turtle. And the displacement, I'm going to represent this with a delta x. And remember that displacement is the final position minus the initial position. You can find the displacement between any two times here. We're just going to find it, for simplicity's sake, for the total time shown on the graph. But I could have found it between 0 and like 4 seconds. Let's just do 0 to 10, the whole thing. So what's the final position? The final position would be the position the turtle has at 10 seconds. She was at 3 meters at 10 seconds, because I read the graph right there, minus initially, because we're considering the total time, at 0 seconds, turtle was also at 3. That means the total displacement was 0, and that makes sense because this turtle started at 3, rocketed back to 5, well, actually started at 3, stood there for a second or two, rocketed back to 5, rocketed back to 3, ended at the same place she started, no total displacement. What else could we find? We could figure out the total distance. So the total distance traveled, remember distance is the sum of all the path lengths traveled. So for this first path length, there was no distance traveled. That was the awkward part. We're not going to talk about that because it might hurt her feelings. Then, all right, so this is 0 meters plus between 2 seconds and 4 seconds, turtle went from 3 to 5. That's a distance traveled of 8 meters. And should we make that negative? Nope. Distance is always positive. We make all these path lengths positive and we add them all up. So 8 meters, because the turtle went from 3 all the way back to 5. That's a total distance of 8 meters traveled. Plus, between 4 seconds and 10 seconds, the turtle made it from negative 5 meters all the way back to 3 meters. That means she traveled another 8 meters. That means in total, the total distance traveled was 16 meters for the whole trip. Again, you could have found this for 2 points, any 2 points on here. All right, what else can you figure out? You can figure out the, say, average velocity. Sometimes people represent that with a bar. Sometimes they just say VAVG. Oops, AVG, that is sloppy. AVG. What does this mean? Remember, average velocity is the displacement per time. And let's find the total. All right, so we're finding the total values here. So the total average velocity, well, I need the total displacement. I already found that. Total displacement was 0 for the whole trip. So this is 0 meters divided by, it doesn't really matter now, but 10 seconds was the time it took for that entire displacement. Oh, not meters, 10 seconds. So this equals 0. There's no total average velocity. The average velocity for the entire trip was 0 because the turtle had no total displacement. How about average speed? So the average speed, I'm just going to write it as average speed. Maybe you'll see it as an S with a bar, maybe an S with an AVG. I don't know. Physicists use all kinds of letters. You never know what you're going to get. But the average speed is defined to be the distance per time. And again, let's try to find the total average speed for the whole 10 seconds. That's not too bad because I already found the total distance. That was 16 meters. So 16 meters divided by the total time. It took 10 seconds for that entire trip. This turtle, she was going 1.6 meters per second on average. That was her average speed. Probably would have been a little higher if she didn't have that technical difficulty here at the beginning. All right, we can figure out more than this though. We can figure out the instantaneous velocity. Maybe you'll see it as VINST. Maybe you just see it as V because this is usually what we're talking about when we're talking about velocity. We're talking about the instantaneous value a lot. What is this? Here's the key idea. In fact, this is maybe the most important idea of this whole video. To find the instantaneous velocity, when given a position versus time graph, you look at the slope because it turns out the slope of a position versus time graph is the velocity in that direction. So since we had a horizontal position graph versus time, this slope is going to give us the velocity in the x direction. And not only that, if we find the average slope, we get the average velocity. And if we find the instantaneous slope, we're going to get the instantaneous velocity. So how do I do that? How do I find the instantaneous slope? Well, in general, if you got a curved graph, you're going to have to use calculus. But we're in luck here because look at these lines. They're all straight. And what that means is that the average slope between any 2 points on one of these lines is going to equal the instantaneous slope at any point on the line. So let's make this specific. Let's say we want to find the instantaneous velocity at, 3 seconds. Pick any point, 3 seconds. How do we do that? Well, we got to figure out what we mean. By instantaneous velocity, we mean the velocity at 3 seconds. Slope here, but I got to go to the graph. So I take my 3, I go down to the graph. I want to know what the instantaneous slope was at that point right there. Let me draw on top of this thing here. I want to know what the slope was right there. How do I do that? Well, I told you the key is that the average slope between any 2 points on this line, so I can pick these two if I want, the average slope between these 2 points is going to equal the instantaneous slope at any point because look at this slope isn't changing. Slope's the same the whole way. And if you take the average of a bunch of quantities that are exactly the same, you're just going to get the same value as any one of these quantities. That was a complicated way of saying if you took the average of 8 and 8 and 8 and 8, what are you going to get? The average value of those is 8, which is the same as any one of these values. So if you ever have a graph that's a straight line, you're in luck. You don't need calculus. You can find the average velocity by you can find the instantaneous slope at any point by taking the average velocity between any 2 points. I'm picking these two. Why these two? Because they're convenient. Look at, I know exactly where they're at. That's 3 and 2. And this one's -5 and 4. You might wonder why. Why is this true? Why is the velocity equal to the slope? Well, remember from math class, slope was the rise over the run. And you might have seen that as, okay, y2, this is math class here, minus y1 over x2 minus x1. But you saw it like that because in math class, typically the vertical axis was always y, and the horizontal axis was always x. But this is physics. Our horizontal axis isn't x. Our horizontal axis is t. And our vertical axis is what we're calling x. So for physics class, the slope of this graph, particularly, the rise, in this case, is this axis, so it's going to be x2 minus x1. Over the run, well, that's going to be t2 minus t1. All right, so how do we do this? Well, this is point 2, this is point 1. How do you know? How come this isn't 2 and that's 1? The point further in time is the one you choose as the second point. So at 4 seconds and -5 meters, that's our point 2. All right, so x2, that would be -5 because I just read my graph at point 2. That's -5. So I got -5 meters minus x1. That's this. Don't make x1 4. That's a time. That's not a that's not a position. So at point 1, the horizontal position was 3, so +3. But the negative's here because the negative's in the formula. And then divided by time 2, that was 4 seconds. And minus t1 was, let's see, 2 seconds. And if you solve this thing, -5 and -3 is -8. Divided by 2 seconds, oops, can't forget my units. Oh, look at that, I got -4 meters per second. That was the instantaneous velocity at 3 seconds, -4 meters per second. Negative because the turtle was going backwards. Remember, that was the awkward. She turned on the reverse booster instead of the forward booster. Negative and 4 because look at going 4 meters every second. Made it 8 meters in 2 seconds. That means she was going 4 meters per second on average. And since it's a straight line, that was the rate she was going at any moment. Beautiful. All right, that would have been, if the follow-up question is, what is it at 2.4 seconds? Don't get concerned. Look, it's the same everywhere. It'd be the same answer, -4 meters per second for this whole line. What else can we figure out? One last thing. Let's say you were asked, what's the instantaneous speed at a point? So I'm going to write that as S-I-N-S-T, instantaneous speed, or just S, because that's usually what we mean by speed, equals, well, absolute value of the instantaneous velocity. So now here I've got to make an assumption. This is going to get a little subtle. If all we're given is a horizontal position graph, we don't really know about the vertical position. This turtle could have gone back and forth, or the turtle could have been like flying upward as she went back and forth. And if the horizontal location was the same the whole way, this would have looked exactly the same regardless of whether the turtle had any vertical motion at all. So we've got to be careful because the speed is the magnitude of the total velocity. This is just the velocity in the x direction. So we're going to make an assumption. I'm going to assume this turtle was just moving horizontally. This turtle didn't have any vertical motion. She's not ready for that yet. All right, so how do you get this? The speed is just the absolute value, the magnitude of the instantaneous velocity. And if this is the only component of velocity, then I can just figure this out pretty easy by saying that I got to give you a time. Haha, makes no sense to say instantaneous speed. I got to say instantaneous speed at a given moment because the instantaneous speed here was 0. The instantaneous speed at this point would have been what? Well, it would have been the absolute value of this, so it would have been +4 meters per second. That would have been the instantaneous speed at 3 seconds, or any time between 2 to 4 seconds, really. Whew, that was a lot. I told you there was a lot in there. So, recapping really quick, the value of a horizontal position versus time graph gives you the horizontal position, surprise, surprise. The slope of a horizontal position versus time graph gives you the velocity in the x direction. The average slope gives you the average velocity. The instantaneous slope gives you the instantaneous velocity, and if it's a straight line with no curvature, these are going to be the same on any given line. They weren't the same here. You're like, what? Hold on, these aren't the same. Well, that's because I averaged over this whole thing right here. I took the average velocity over the whole time. and this slope was changing. So what I really got was the average of all of these, and that's why these weren't equal. But if I constrain myself to just the average value along a line that doesn't change its slope, that will equal the instantaneous slope at any point. And the instantaneous speed is the magnitude of the instantaneous velocity, assuming you only had motion in one direction.